Well, hi there, guys. I'm going to make a video today about L'Hopital's rule, um, and a this rule really shouldn't be attributed to L'Hopital. It really should be attributed to Jacob Bernoulli. Well, we've talked about this in class. L'Hopital here, he jacked this from Bernoulli and published it as his own work, which is, you know, rather seedy. So I don't know why we still attribute it to him, but that guy's a thief. Anyway, well, he only lived 43 years, so I shouldn't bust on him too much. But this rule is really, really, really easy to use. It is obvious when you're supposed to use it. And so this is going to be something nice. It'll be a couple points on the AP test. And we are going to use this anytime we get an indeterminate form. So really the hardest part is knowing that you get an indeterminate form. Okay, L'Hopital's rule only is used when you are dealing with a limit. So that's pretty simple. And on top of that, it's going to come up anytime you get a limit. When you plug this little number in for x and you get 0 over 0, and again here you get 0 over 0, that's the most common one. But it can be used for other ones we're going to look at in a minute. L'Hopital's rule basically comes from a really simple proof. And it says that if you have this function f and also this function g, I'll call that one f and I'll call that one g, and I'll call this point c here. So if you have a limit as x approaches c of f of x divided by g of x, and as x approaches c, if both of these y values are 0 over 0, then you can replace them with their tangent line equations. We can say that f of x is approximately equal to f of c plus f prime of c times x minus c. And of course g of x can also be replaced with its tangent line approximation, g of c plus g prime of c times x minus c. And so since we can replace these functions, if they're differentiable, with their tangent line approximations, let's look at the division here. F of c and g of c, we just saw both went to 0. And the x minus c cancel, and we can see that if we get 0 over 0, we can look at the quotient of their derivatives instead of the quotient of their original functions. So back to this original problem, limit as x approaches 2 of x squared minus 4 over x minus 2. We got 0 over 0, which is indeterminate, so what we can do is we can take the rate of change of the top, that's called the derivative, by the way, the rate of change, and then the rate of change of the bottom, and we can try the limit again. And then we plug in 2, and we get 4. Notice there's no reason to take the derivative again because we have an answer to our limit. And if you were to graph this, you would see that the y value as you approach 2 of this function, this rational function, would be 4. Same thing is true on this second one. We could take the rate of change, that's the derivative of the top, and the rate of change of the bottom, and try the limit again, and we get 1. It's really useful, very obvious when you're supposed to use it. When you get 0 over 0 or an indeterminate form, take the derivative of the bottom and the derivative of the top, and then try the limit again. Pretty simple. Alright, this is a formalization of it. We have to say that they're differentiable, except possibly at that simple point. And this is all you need to know. If you get some kind of 0 over 0 or indeterminate form, in the second we're looking at infinity over infinity as well, you can take the limit of their derivatives instead. So the rest of this is pretty wordy, so we're not going to go over that. Alright, so let's take a look at another example here. I think we've already seen this one. Let's take a look at infinity over infinity. If we were to plug in infinity into this e to the x over x, we would get infinity over infinity. This is indeterminate. This is not 1 necessarily. So what we're going to do is we're going to take the derivative of the top and the derivative of the bottom, and we're going to try the limit again. And here we get e to the infinity over 1, which is infinity. And this is our first dive into something that's really interesting, and I absolutely love our next unit because it's pretty cool, it's pretty intense, just because it's thought-provoking. But here, the numerator's infinity has a higher power then the denominator's infinity. So this infinity is more powerful. And the reason it is because the rate of change, or the rate of growth of the exponential, is way more powerful than the rate of growth of a polynomial. And so if you were to divide these and look way out to the right on the x-axis, this graph would just explode. Okay, let's try another one. Limit as x approaches 0, 1 minus cosine x over x plus x squared. If we plug in 0 for x, we're going to get 1 minus, cosine 0 is 1, 1 minus 1 over 0 plus 0 squared. So we're going to get 0 over 0. So what we're going to do is we're going to take the derivative of the top and bottom. The derivative of the top is going to be positive sine x. The derivative of the bottom is 1 plus 2x. And we're going to take the limit as x approaches 0. We plug in 0 for x, and we get, that arrow is supposed to be pointing right here, we get the sine of 0, which of course is 0, over 1. And now we're done. There's no reason to keep taking derivatives. This has an answer that's just 0. Alright, one last example is you can apply L'Hopital's rule more than once if necessary. So if we plug in 0 for x here, we're going to get the square root of 1 minus this is 0 over 0. So we're going to take the derivative of the top and bottom. The derivative of the top is 1 over 2 square roots of 1 plus x minus 1 half. The derivative of the bottom is 2x. And when we plug in 0 this time, we're going to get 0 over 0 again. And if you get an indeterminate form, you can just continue to apply L'Hopital's rule. So let's take a look at this part right here, because this might be confusing to some people. We can rewrite that as 1 half times 1 plus x to the negative 1 half power. Might be easier for you to see this derivative. So this becomes negative 1/4 times 1 plus x to the negative 3 halves power over 2. And if we take the limit as x approaches 0 of this, we plug in 0 for x. 1 to any power is 1, and we get negative 1/8. So there is an example of using L'Hopital's rule more than once. Last thing is, we're going to look at that one right now. Different kinds of indeterminate forms. We'll come back here. There we go. Some other kinds of indeterminate forms are 1 to the infinity, or infinity times 0, and that will come up as well in the next couple of weeks. So anyway, it's to recap, this is a really easy application. Anytime you get 0 over 0, that's what comes up the most, or infinity over infinity, you're going to take the derivative of the top and the derivative of the bottom and try the limit again. It's pretty simple. So I will see you guys tomorrow.